Hi, welcome back. We've been combing through numerical charts looking for patterns that might reveal a proof to the 3n+1 conjecture. You might wonder if a computer could help us look for patterns. Well, I'm going to describe an amazing computer-based attack on the 3n+1 problem, published in 2021 by Yolcu, Aaronson, and Heule. Everything in this episode comes from their super accessible archive paper. To get started, let's imagine the world of 3n+1 trajectories, along with a corresponding mirror world. Suppose there's a function, g of x, that maps real-world numbers onto their mirror-world counterparts. So if you look here, while numbers in the real 3n+1 world gyrate up and down, their counterparts in the mirror world steadily march downwards. So they'll eventually have to stop, and the corresponding 3n+1 trajectory will also have to stop, which would allow us to prove the 3n+1 conjecture. But unfortunately, we don't have a formula for this g of x, so it's not a proof yet. But it's an idea for a proof, which we'll come back to in a couple of minutes. But first, remember in episode 2, we looked at a 3n+1 machine made of colored marbles and pool cues based on a tag system that Lisbeth DeMol came up with in 2008. So pick a start number like 3, and by applying just 3 rules, we could get 5 red marbles, and then 8 and 4, 2, and 1. So this system simulates 3n+1. Now, there's one problem. If we apply the rules to a number like 31, we're going to need thousands of marbles. But we can save a ton of marbles if we encode the numbers in binary instead. So for example, instead of 38 red marbles, we start with this. Now we need a new set of rules to simulate 3n+1. Well, 38 is even, so we need to divide it in half, which is easy. We just delete the last 0 with a rule that says 0 bracket goes to bracket. Now 19 is odd, so we need to multiply it by 3. But dang it, that's hard to do in binary. Now if 19 were in ternary, we could triple it by adding a 0 to the end, or actually a 1 to the end, to get 3n+1. But how do we divide 58 in half to get 29? Well, dang it, that's hard in ternary. So Yolcu et al.'s first idea is a mixed base way of writing down numbers. They use the symbols TF, 0, 1, 2, open bracket, and close bracket, where each symbol has a little linear function. So let's take a string like this. The open bracket has the value 1. The O means whatever's to my left multiplied by 3. The F means multiply that by 2. The 1 means multiply by 3 and add 1. So this string means 19. Here's a simpler example. Bracket T bracket means 3. Now let's execute the 3n+1 procedure on that by applying rules. Well, 3 is odd, so what rule will multiply it by 3, add 1, and cut it in half? Well, it's easy. Rule number 1 says replace T bracket with 2 bracket. Now instead of 2 times 1 plus 1, we get 3 times 1 plus 2, which is 5, the next number in the sequence. Now 5 is also odd, so unfortunately you can't do the same rule though. But no problem, we apply rule number 2, which replaces bracket 2 with bracket ft, which amazingly doesn't change the value because bracket ft bracket still means 5. And now we can apply rule number 1 to get bracket f2 bracket, which is 8, the next number after 5. And with just 11 rules, we can simulate any 3n+1 trajectory on these very compact numbers. This trajectory finishes 8, 8, 4, 2, 1. Now, if we interpret strings as numbers, then we're in this world of 3n+1 trajectories where the numbers bounce up and down. So now for their second big idea, that there's a mirror world that interprets the same strings, but in a different way. And in the mirror world, the meaning of a string isn't just a number, it's a pair of numbers, a vector of length 2. So for example, bracket ft bracket isn't 5, it's the vector 68, 0. So we still assign a simple function to each symbol, but these functions need to map vectors onto vectors. So before we had t as 2x plus 1, now we have t as this matrix times some vector x plus this vector. So for example, t applied to 2, 2 gives 9, 15. And so to get the meaning of something like bracket T bracket, this time we're going to go backwards through the string. So close bracket is 2, 2, and we apply t to it, getting 915, and then we apply open bracket to that, and we get 840. Okay, and this next string, we'll skip it, the steps, but it means 780. The next one, 690, 620, and so on. So while in the real world of 3n+1, the numbers jump up and down, in the mirror world, these vectors seem to only go down. So if the mirror sequence has to eventually stop, that means the corresponding sequence in the real world also has to stop, which would mean the 3n+1 conjecture is true. Okay, so that's their second idea. Now, whether the mirror world sequences really go down for any sequence of rules depends entirely on the matrices. So given these 11 rules, we need to select matrices that ensure any vector is going to get smaller when we apply any rule to it. And that gives a very clear finite set of requirements. And so their third idea is to apply an automatic computer search for matrices that satisfy those requirements. And here are the matrices that the computer came up with. So whenever we apply any rule to any string, the mirror world sequence is guaranteed to decrease, unless we apply rule number 11. Now, if we start with 3, we never need rule number 11, so things go down. But whenever we need to apply rule number 11, the mirror world sequence might jump back up, and then go down and back up unpredictably, just like in the real world. It's not that rule number 11 is especially hard. They can find matrices that work for any subset of 10 rules. So the 3n+1 conjecture is still unresolved. But combining a mirror world with an automated computer search is a really cool idea. Maybe if the computer worked harder, it could find matrices that work for all 11 rules. Or maybe we could ask the computer to consider functions that are more powerful than matrix multiplication. Or maybe we give the computer some expert knowledge about 3n+1. Of course, maybe the 3n+1 conjecture is false, but I think computers have good potential for speeding up a proof either way. Okay, see you next time.